All right, good morning, everyone. Happy Friday. Today what we're looking at is lesson 30.10, which deals with diffraction and interference of light. And this lesson can be found on page 7 of the current lesson handout. So to begin with, we're going to talk about what diffraction of a wave is. And for the next little while, at least, I'm going to be talking about mechanical waves because it's easier to understand diffraction and interference when it comes to mechanical waves. We're going to end up saying in the end that light also experiences diffraction and interference. It's harder to imagine what's physically happening with light in order for it to diffract and interfere, which is why we start off by looking at mechanical waves, which is something physical, something we can visualize quite easily. So what diffraction of a wave is when a wave passes through an opening, it spreads out as it goes through the opening. So as an illustration here, what we're looking at in this diagram is a series of ripples on the left-hand side of the diagram. And those ripples, you can think of them as being the crests of a wave. They're traveling left to right. And then we have this barrier in the middle of the diagram. And the barrier has an opening in it. So some of the wave, not much of the wave, but some of the wave will make it through. And the little piece of the wave that makes it through continues traveling in the direction it was originally traveling, but some of that little piece ends up traveling in this direction. Some of it travels in this direction. Some of it travels in this direction. It travels in a whole bunch of directions. In other words, it spreads out. So there's a couple of ways to explain what this means. One of them is to say that if this were a sound wave on the left-hand side, you over here on the right-hand side would still be able to hear it if you were up here. You would still be able to hear it in your ears because the sound wave, when it passed through the opening, spread out. You wouldn't have to be directly across from the opening. One thing I want to point out to you, though, is that if you were up in this location at the top, you would be able to hear it, and you would be able to hear it here, and you would also be able to hear it here, but the person who is directly across from the opening would hear it the loudest. So as the wave spreads out and moves further and further away from the original path, it gets dimmer and dimmer and dimmer. So that if the actual sound was somebody yelling, "Hey," then this person would hear it. This person would hear it, but it would be quieter. And the person at the top would hear it, but it would be very quiet. So there's a dilution of the energy. The sound energy gets diluted. You get the most energy directly across from the opening, and as you get further and further away from the opening, you get less and less energy. I hope it's understood that it goes in the other direction as well in terms of the energy dissipating or the energy getting to be less and less. If this were a water wave, and I have a little clipping here that I found in Google Earth. I was scouring the coastlines in Google Earth. This is called a breakwater, and it's in a region of the world where the waves are really quite energetic. So this is by a beach where you don't want the waves to be so energetic that it causes chaos for the people on the beach. However, you still want some of the wave energy to end up reaching the beach. So the breakwater takes these water waves that are traveling, in this case, towards the top of the page, and it allows some of the wave energy through, but it blocks out a lot of it. Along the same lines as what I described if it were a sound wave, if this is a water wave, and you are sitting on a little floating chair here, drinking your pina colada because you're on vacation, your chair is going to be bobbing up and down in the water. And the reason is some of the wave energy that goes through that opening is going to travel in your direction. However, if instead you were sitting over here, your chair would be bobbing up and down with more energy. And if you were sitting over here, your chair would be bobbing up and down with even more energy. And I'm going to remove all of these arrows on this diagram now to show you something. And that's that you can actually see directly across from the opening, the wave has more energy. When you take a look at the color of the wave, it's white directly across from the opening. It has a lot more whiteness to it. And that's telling me that the water is really, really moving around directly across. If you look in this region, there's a lot more action happening in the water than there is in this region or in this region. And if you look over here, although faint, you can still see some action, but it is not nearly as much. We could also describe the distribution of energy by looking at a graph. I've got a grid here that has energy measured on the vertical axis and position on the horizontal axis. We know that there's the most energy directly across from the opening, which is right here. And we know that as you are to the left of it or to the right of it, there is less energy. So the graph would end up looking something like that. I want to point out something to you that is going to be important for later. If a wave passes through an opening, it diffracts, it spreads out. However, this is common sense, by the way. If I stood on the other side of this opening and I fired a bunch of ping pong balls or marbles or particles downward through the opening, then what would happen is they would all pile up in one area. And if they all pile up in one area, then what the graph looks like here is essentially this. There's nothing, then there's this lump of energy, and then there's nothing. And the point I want to make here is that particles do not diffract. So the fact that a wave diffracts is one of the defining features of it being a wave. Particles do not diffract, but waves do diffract. So this is what the energy diagram would look like if we had particles moving through the opening. So getting back to our notes, the longer the wavelength, the more severe the spreading out of the wave energy is. And again, this is something that particles do not do. But I want to address this statement that the longer the wavelength, the more severe the diffraction is. If I had 3 different waves, and I've color-coded the wavelengths here, I'm using a purple wavelength, a green wavelength, and a red wavelength, and they all pass through the same opening, the purple wave will diffract. The green wave will diffract, but it will diffract more than the purple wave because the wavelength is longer. This is the rule of diffraction. The red wave, which has an even longer wavelength, is going to diffract the most. And I hope it's not lost on you that I'm using these colors because when we start to talk about light, light has colors. And purple light has a shorter wavelength than green light. And green light has a shorter wavelength than red light. Now, waves can also interfere. What interference of waves is the fact that waves have the ability to pass through each other. And if you have 2 things that pass through each other, then there has to be a point in time where they are in the same place at the same time. And that is called the principle of superposition. Waves can exist in the same space at the same time. This is something that particles do not do. This is why we have collision insurance on our vehicles. Now, when 2 waves are in the same place at the same time, one of 2 things can happen. They can meet in phase, and what in phase means is that one wave is working to push the medium in a direction, and the other wave happens to be trying to push the medium in the same direction as the first. We call this in phase. And in Physics 20, you might have been taught that this is when waves meet, where a crest of one wave meets the crest of another wave. If they do meet in phase, the resulting wave is a temporary amplification of the wave energy in that region. If the waves meet so that one of the waves is trying to push the medium in one direction, but the other wave is trying to push the medium in the other direction, then that is called out of phase. And in Physics 20, you're taught essentially that that is when you have the crest of a wave meeting the trough of another wave. What result we get is called destructive interference, and it's a temporary reduction of the wave energy in that region. So I'd like to show you a couple of very, very brief videos. These are old videos. I don't know why anybody hasn't bothered to make newer ones. This is on a loop, so it's going to repeat. You have two waves that are moving in opposite directions, and they are passing through each other. And while they're on top of each other, that's the point of superposition. So the first thing I want to do is pause the video at that instant where they're right on top of each other, to point out to you that the amplitude of the wave here is bigger than the amplitude of each of the separate waves before. And I'll let you watch that just a couple more times. We have these two low amplitude waves coming together, producing a high amplitude wave momentarily. Now, I know that there's an illusion here that these two waves do not appear to be going through each other. They appear to be bouncing off of each other. But to illustrate to you that they definitely are passing through each other, I have a different one. We have a large amplitude wave coming in from the right. We have a low amplitude wave coming in from the left. They pass through each other. We can tell that they pass through each other because afterwards, the bigger amplitude wave is still traveling to the left, and the smaller amplitude wave is still traveling to the right. And again, at that instant where they're on top of each other, you have an increased amplitude. Very similar kind of idea here, except these two waves are out of phase. You have a wave that's pushing the spring towards the top of the screen. You have another wave that's pushing it towards the bottom of the screen. And at that instant in time, it's not perfect, but I'll try to stop it where they are on top of each other. At that instant in time, I'll do that again. At that instant in time where they're on top of each other, there's a reduced amount of energy temporarily in the wave. Of course, once they pass through each other, that energy comes back. So that is an example of what we mean by superposition of mechanical waves, when waves are in phase and when they're out of phase. Now, what double slit interference is what happens when a wave passes through two openings. Now, when the wave passes through each of the two openings, the wave will spread out. So you get this rippling effect of the diffraction of the wave through the opening on the left, and you get an identical rippling effect of the diffraction of the wave passing through the opening on the right. The end result is you get this pattern. These waves are interfering and you get an interference pattern. If we were throwing a bunch of marbles through the two openings at the top, you would expect to get two piles of marbles at the bottom of the page. But what happens here is you get energy that increases and decreases in magnitude depending on where you are. And if you were in school, there's a great demonstration that I do where at the top of the page, what I would have in the classroom are two speakers. And I have those speakers connected to an audio source that's a very high-pitched audio source. It's actually kind of an annoying thing to listen to. But what we do then is you stand at the other side of the room and you walk slowly from one end of the room to the other end of the room. And what you discover is there are places where you can hear the sound very, very loudly, and there are actually places, it's hard to believe, where you can't hear the sound at all. If you put your ear in just the right position, it's dead quiet. And what we discover when we do this is that if you walk across the room and you mark off the places where there is the most sound and where there is less sound, we actually use a decibel meter to measure the sound levels. You'll discover that when you hold the decibel meter here, directly across from the two openings, you get the most sound energy. But if you go a little bit to the left of it or a little bit to the right of it, you discover that you don't get any sound energy. And if you go a little bit further again to the left or the right, you do get some sound energy, but it's not as much as you got in the middle. And then it drops off to 0 again. And then it increases again to a maximum, but the maximum again is not as big as the maximum before. And the same thing happens on the other side. And what you discover after plotting these points is you get a distribution of energy that looks something like this. And literally, as you walk across the room, the sound gets louder and then quieter, and then even louder and then quieter, and then even louder and then quieter, and then it starts doing the reverse. If these were marbles being thrown through those two openings, you'd get two piles of energy on the other side of the room. You wouldn't get this interference pattern. So this is what an interference pattern is in terms of energy. Now, it turns out that when light passes through two tiny openings, you don't get two dots of light on the other side. If you did, that would be telling us that light is behaving like marbles or ping pong balls. It would tell us that light is behaving like a particle. But what we see when we pass the light through two tiny openings is an interference pattern. We see a distribution of energy where you have a bright dot of light and then you have two other bright dots of light on both sides, and in between you have nothing. And as you get further and further away from that central bright dot, the bright dots become dimmer and dimmer. In other words, you get this energy pattern that we talked about here with the water waves, you get it with visible light. And that's what I'm going to show you right now. I'm just going to show you very quickly here what I'm talking about by shining different lasers through a diffraction grating. A diffraction grating is just a piece of glass that has a bunch of tiny openings on it. So we'll take a look at that and then we'll resume the lesson. Okay, what we're looking at here is the interference pattern formed when we have a red laser light passing through a diffraction grating. What a diffraction grating is simply a source of two tiny, tiny openings that are very close together. And what's happening is the light is passing through each of those two openings. The light is spreading out as it passes through each of the two openings. And now each of those two spread out sources of light will interfere when they overlap, and you get that interference pattern. Let's talk about some terminology first. All of these dots that you're seeing on the screen are called maxima. The word maxima is plural for maximum. This brightest dot is called the central maximum. This is called the n equals 1 maximum, and this is the n equals 1 maximum. You'll notice that the brightness of the n equals 1 maxima is not as great as the brightness of the central maximum. By the way, the n value for the central maximum is 0. And if you look at the n equals 2 maximum, which is in this position, and another n equals 2 maximum in this position, they are even dimmer. And we talked about that in the video. I think I used as an analogy sound waves, but we said that the further away the person was from the original path of the sound wave, the less they would be able to hear. So as you get further and further away from the center, it dims out. The point halfway between the central maximum and the n equals 1 maximum is called a minimum, and it's referred to as the n equals 0.5 minimum. This would be the n equals 1.5 minimum. This would be the n equals 2.5 minimum. So n is 0.51, 1.52, 2.53 if you can see it, and it's the same on the other side. One other thing before we take a look at other colors, there are other words that we use rather than maximum and minimum. What we can do, instead of calling this the central maximum, is we can call it the central antinode. And you need to associate the word antinode with maximum or bright spot. Instead of calling this the n equals 0.5 minimum, we can call it the n equals 0.5 node, N-O-D-E. And you need to associate the word node with no energy. Okay, in the video we learned that longer wavelengths diffract more. Now don't forget, the diffraction is really spreading out the light. So these dots are a certain distance apart because the red light diffracts a certain amount. Red light has a long wavelength. If I were to take a look now at the interference pattern, but I were to use a green laser light, the prediction would be that the dots should be closer together because green doesn't diffract as much. It doesn't spread out as much. So before I put the green laser on there, I don't know if you can tell or if you've noticed, but there's a meter stick, and I'm going to estimate the distance from the central maximum to the n equals 1 to the right of it, and I would say that it's pretty close to about 6.5 centimeters. So the distance between the n equals 1 and the central maximum with red light is 6.5 centimeters. What we are looking at now is green light, and the green central maximum is in this location, and then the n equals 1 is in this location. By the way, the green light is a lot brighter. That just has to do with the laser. It has nothing to do with the wavelength of the light. And if I were to estimate the distance between the central maximum and the n equals 1 this time, I would say that it's around 5 centimeters. And you can probably tell just by looking, the dots are closer together. I'm going to replace it now with violet light, and violet light has the shortest wavelength, so it should be affected the least, which means the dots should be really close together. So now we're looking at the violet laser passing through the diffraction grating. The violet laser is quite dim, and it's not as vibrant of a color as green or red. But now if I look at the meter stick and I do my best to estimate the distance from the central maximum to the n equals 1, I would probably say it's 4 centimeters. So a couple of lessons here about this quick demonstration. One, you need to become familiar with the terminology of maxima or antinodes and how those maxima relate to the value of n. And the other part is you need to know what a node is and how those relate to the value of n. As well, you need to know that longer wavelengths are affected more by diffraction. Now, there are two formulas that describe the relationship between all of the measurements that we're going to be making here in a minute. And we'll get to what all of these letters mean, but I want you to make a note here right now that this first formula on the left is only valid if you have an angle that's less than about 10 degrees. This is the only place I've ever encountered in physics where we have a formula that isn't a good formula. And the fact of the matter is the formula on the right always works. It doesn't matter what the angle is. So we're going to encounter at least one example today where we are not allowed to use the formula on the left, even though we probably would want to because all of the variables in the question match the variables in this equation. If we had more time, I would go through an explanation of why one of these formulas is good sometimes, but it's not good all of the time. But we don't, so I'm not going to worry about it. Okay, I'm back looking now at a red interference pattern. I've zoomed in a little bit and I want to talk briefly here about what the variables represent in the equations. Both equations have lambda in them, so lambda is obviously the wavelength of light. Both equations have d in them. What d is the distance between the openings in the diffraction grating. One of the equations has x in it, and what x is a distance from the central maximum to whatever image you're talking about. So if you were doing some work with the formula and you were talking about this image, which is the n equals 1 maximum, then x would be however large this distance is. from the central maximum to the n equals 1 maximum would be the value of x, but that's only the value of x if you're going to use n equals 1. If you were going to put n equals 2 into the formula, then x is the distance from the n equals 2 maximum to the central maximum. So if you use this distance for x, you're going to use n equals 2. If you wanted to put in n equals 1.5, then you would have to measure the distance from this minimum to the central maximum. If you were to use the n equals 3, and I'm not sure that you can see it on this side or on this side, but if you were to use the n equals 3, there's a bright spot there, you would have to measure this whole distance for x. So x and n go together. When you decide on an n value, that automatically determines what you're going to measure for x. What L is the distance from the diffraction grating to the screen. So if we were to measure the distance from the bottom of this screen all the way back to the diffraction grating, that distance would be L. What theta is an angle between this line and the line that connects the diffraction grating to the image you're talking about. So if you're talking about the n equals 2 image, if we were to extend a line back from the n equals 2 image to the diffraction grating, and we measured the angle between that line and this line, that would be theta. So lambda is the wavelength, d is the distance between the openings, n is the location of the image or the dark spot or the part of the pattern that you're talking about. So n is a number. X is a measurement that takes you to that location. L is the distance between the screen and the diffraction grating. And theta is the angle from the perpendicular distance over to whatever point you're talking about. Okay, so here's a top-down view of what we were just looking at in the video. Again, the regions where you get a bright spot are called maxima. That's the plural of maximum. Sometimes they are called bright spots. Sometimes they are called antinodes, and that gets a little bit tricky. An antinode is a region where there is a lot of energy. And then the points halfway in between where you have deadness, those are called minima or nodes. And I just remember a node has no energy because the word node starts off with the word no. What are all of these variables? Again, lambda is the wavelength of light that's going through the openings. D is the distance between the openings. Theta is the angle to whatever image you're looking at on the screen. L is how far apart the diffraction grating or openings are from the screen. And then we have x and n. X and n go together. So for example, if you were talking about using in the formula information about this position in the interference pattern, then you have to use this value of x. If, on the other hand, you were going to be concerning yourself with this position, then the value of x that you would have to use would be that distance. So they go hand in hand. If you choose a particular point for x, you have to choose the corresponding point for n. N equals 1 goes with the blue x. N equals 2 goes with the yellow x. So let's take a look at a couple of questions now. Monochromatic light, all that means is the light has one very specific color or wavelength. In other words, it's probably a laser. Is incident on a set of double slits, and the distance between the slits, which is d, is 0.3 millimeters, so 0.3 times 10 to the negative 3 meters. We are looking at the first bright fringe. There's another word that we could use instead of bright spot or maximum or antinode. We can say the first bright fringe. That's n equals 1. It's located at an angle of 0.08 degrees away from the central antinode, so that's theta. And then the question is, what is the wavelength of light? There's three questions that we're trying to answer here. What's the wavelength, and then what would the angles be for the n equals 2 and the n equals 3? Well, the only formula that would really make sense to use here, which would be d sine theta over n, happens to be the formula that always works. So this is a valid formula. We never have to question whether we're allowed to use this formula or not. We're going to take d, which is 0.0003, multiplied by sine of the angle, and then divide by n, which is 1, and this is going to give us lambda. Make sure you're in degrees, of course. Make sure you close the brackets on the argument for sine. I guess we don't really need to say divided by 1. So I'm getting 4.19 times 10 to the negative 7 meters. Which is 419 nanometers, which if I had to take a stab, I would say it's violet light. If you said blue, that would be fine, but it's at the short wavelength end of the visible light spectrum. The other question now asks us to determine what would the angle be if n was 2 and if n was 3. Well, we're just going to go back to that same formula. Lambda equals d sine theta over n. And we're going to solve for theta. And because I have two different calculations I'm going to do, I think what I would prefer to do here is rearrange for sine of theta. Sine of theta equals n lambda over d. So I can do that now for each of the two. I can go 2 times lambda over my d. That will be sine of the first angle. And then I can calculate 3 times lambda over d, which of course is going to be sine of the other angle for the n equals 3. And we already know what d is, and we already know what lambda is equal to, so I don't think there's any need for us to write this down again. In fact, lambda is still on my calculator. I'm going to store my wavelength as a, just so that I can retrieve it later quite easily. So what am I going to have for the first angle? I'm going to have to take 2 times the wavelength and divide by d, which was 0.0003. Then I have to take the inverse sine of the answer. So the second angle is at about 0.16 degrees. I can repeat that process now and go 3 times the wavelength divided by the d, and take the inverse sine of the answer, and I get about 0.24 degrees. So for the n equals 2, you get an angle of approximately 0.16 degrees, and for the n equals 3, you get an angle of approximately 0.24 degrees. So that's example 1. Let's take a look at example 2. A student is measuring the wavelengths of light emitted by a gas sample, and they direct the light that's emitted from the sample through 2 slits that have a slit separation that's given to you. So you know d is 0.26 times 10 to the negative 3 meters. We get an interference pattern on a screen 3 meters away. That means L is 3. And the distance between the second bright antinode and the central antinode, that distance, which is x in the formula, is 1.18 multiplied by 10 to the negative 2 meters. And you're asked to determine the wavelength, so your mind will probably say, I'm going to use xd over nl. But we can't just use that formula all the time. That formula, remember, is only good if the angle is less than 10 degrees. So we need to take a little bit of a step back from the formula for a second and ask ourselves if the angle is less than 10 degrees. What we have is a diffraction grating on the left. The light passes through the diffraction grating left to right, and it creates an image on a screen over here on the right-hand side of what I'm drawing. And there is a point over here of light that we're interested in. And this distance right in here is 1.18 centimeters. Now the actual beam of light travels from the diffraction grating over to that point, and you were also told that the distance between the diffraction grating and the screen is 3 meters. So the question is that angle less than 10 degrees? Well, we can do a trigonometric calculation here. The 1.18 centimeters is opposite to the angle, and the 3 meters is adjacent. So I can use tangent to find the angle. I'm going to say tangent of the angle is 1.18 over 300. I have to use the same units for both, and I'm choosing to use centimeters for both. Let's see what we get for an angle. Inverse tan of 1.18 divided by 300 gives me a very small angle, less than a degree. So this is approximately 0.2. So this is approximately 0.2 degrees, which is definitely less than 10 degrees. So we are allowed to use this formula. All we're going to do is put x, d, n, and l into that formula. Let's see what happens here. X is 0.0118 times d, which is 0.26 multiplied by 10 to the negative 3, divided by L and N. So divided by, in brackets, N is 2 times L is 3. What I get for a wavelength is 5.11 multiplied by 10 to the negative 7 meters. Or 511 nanometers. And that's the answer to question 2. All right, let's take a look at example 3 now. This is another situation where if we were in the classroom, we actually do this as a demonstration and do the calculations together. We've got 2 microwave generators that are put 15 centimeters apart. And I actually have 2 microwave generators in my classroom that I set up, and I put them at this distance of 15 centimeters apart. And at a distance away from the 2 microwave generators, we're using 70 centimeters in this question, I move a microwave detector back and forth. And if I put the detector at this location, what I discover is that it squawks the loudest. It's got a speaker on it that makes a noise when it detects microwave radiation. And it's very loud. And what I discover is if I put the microwave detector at this location, it's dead quiet. It doesn't make any noise. And when I put it at this location, it squawks loudly again, but not nearly as loudly as it did in the middle. And it will squawk the same on the other side. And then I go to different locations and I show students that you get an interference pattern. So it's not just visible light that can undergo double slit interference. What we have is microwaves originating from an opening in this generator and an opening in this generator. And as those microwaves leave those openings, they spread out, producing the interference pattern. By the way, the 15 centimeters is the distance between the openings, which is D. The 70 centimeters is L. This distance of 23.8 is X. And since it's the second order maximum, we're going to have to use 2 as being equal to N. So what are we asked to find here? Well, we are asked to determine the wavelength of the microwaves. And you know X and D and N and L. But is this a valid formula here? Remember, you can only use if the angle is less than about 10 degrees. Well, we can calculate the angle. By using tangent. We have a right triangle in this diagram. The opposite side is 23.8 and the adjacent side to the angle is 70 centimeters. So let me label theta in here. This is theta, which means tangent of theta is equal to 23.8 over 70, and we can find from that relation theta. Inverse tan of 23.8 divided by 70 gives us a whopping 18.8 degrees. So the answer to the question so far is we're not allowed to use that other formula. We have to use the good formula. But that's okay, because if we're not allowed to use this formula and we have to use lambda equals d sine theta over n, then we need to know theta, but we just calculated theta. We already know what theta is. Theta is that 18.77 degrees. What else do we need to know in this formula? We need to know d. Well, that was 15 centimeters, so 0.15 meters. And the value of n that we're using is 2. So all we need to do is load these three things into that formula to get an answer. Lambda will equal 0.15 multiplied by sine of the 18.77 degrees divided by 2. So I am getting an answer of 0.024 meters. Which is 2.5 centimeters. And when we do this in class, we look at the back of the microwave generators and there's a little specification stated there that tells us the wavelength of the microwaves. And it's what we end up getting in the question. So be very careful here when you're using these two formulas. You may be tempted to use the lambda equals xd over nl formula, but every time you do, every time you're tempted to use that xd over nl equals lambda formula, find the angle first to make sure if you're allowed to. And if you're not, you're going to have to use the other formula. Your daily assignment now is to complete questions 1 through 180. That's not a typo, that's correct. You'll take a look at the assignment and see what it involves. There's not 180 questions. Just a reminder here, you do have another assignment that's due to be turned in on Tuesday that was given to you yesterday. And remember that you have to watch the video that was posted yesterday in order to understand how to do the assignment and also in order for you to collect the data. So don't forget about that. Don't leave it to the last minute. Try to be organized in everything that you're doing. It is Friday though, so have a fantastic weekend and we'll see you on Monday when we move on. Take care, you guys.